All right, folks. Now I want to look at combining series and parallel resistors to create specific resistances that we may need for circuits. So the first example I want to look at is we got an inventory of resistors available to us. So we got 10 ohm, 100 ohm, 256 ohm, a kilo ohm, and 10 kilo ohm resistors, and a limited quantity of each. So say for example, the circuit that we're building, like we got a specific sensitive sensor or something, needs to control current in such a way that I need a resistance of 5 ohms to do that. So obviously, over here in my inventory, I don't have access to a 5 ohm resistor. What combination of resistances can I make to get as close as as close to 5 ohms as I can? Now, we've got two different ways of combining these circuits. We've got series and parallel circuits that we can use to combine them. And so, the easiest one to work with is obviously a series circuit. And you guys know what a series circuit is. I've got, one resistor connected end to end to another resistor. So, you know, that's just the resistor part of the circuit. There's probably batteries and sensors and other stuff in that circuit. This may be high voltage, this may be low voltage. And the question is, can I use a series circuit to help combine to get 5 ohms? Well, the obvious answer here is no. The smallest resistor I've got is 10 ohms. And so if I connected two of these smallest possible resistors, we remember what the equivalent resistance is for a series circuit. That is just adding these two resistances together. So 10 ohms plus 10 ohms, that's going to give me a series resistance of 20 ohms. So just using series circuits, the smallest resistance I can get is 20 ohms, which is obviously not going to get me a smaller value. So that means we're going to have to venture into the realm of parallel resistors, which it's got kind of a weird equation, if you remember what it is, but it will let us get smaller resistance values out of bigger resistors. So, for example, let's take a look at a parallel combination of resistors. And so it's just like the name implies, my two resistors are connected, so they look like they're parallel. So this may be my positive voltage terminal. This may be my negative voltage terminal. I've got other things in the circuit. And so, for example, if I have my 10 ohm resistor here, let's use another 10 ohm resistor here and see what happens. So the equation for an equivalent resistance for two parallel resistors is kind of the one with all the weird fractions. It's 1 over the resistance of one resistor plus 1 over the resistance of the other resistor. And then I want to take the inverse of that fraction. And of course, if I have more than two resistors in parallel, I can add as many 1 over the resistances inside these parentheses as I need. But for two parallel resistors, I got 1/10 plus 1/10. Oh, good. They've got the same common denominator. So that's 2/10. And I've got this little -1 exponent, this inverse. And I'm sure you guys all remember that just means flip the fraction of whatever is inside the parentheses. And so if I do that, I've got 10 over 2. You may need your calculator for this. It's pretty complicated. That's just 5 ohms. Well, that obviously is the resistance that I'm looking for with this circuit. And you can see if I've got two parallel resistors connected, I'm going to get a smaller resistance value than those two resistors. There's actually one more pretty nice feature here. If I've got a parallel resistor, or two parallel resistors, and they are the same resistance, my equivalent resistance is going to be exactly half the resistance of my resistors. So if I got two 10 ohm resistors connected in parallel, that equivalent resistance is going to be 5 ohms, which is what I needed for this particular problem. A nice feature, lets you get a lot of different resistances pretty easily if you can remember this one little trick.